Now let's talk about simultaneous equations. This is the final topic of this semester. In order to define simultaneous equations, let's review what we have learned about multiple causal variables. That is a causal model where there are more than one causal variables that we're interested in. So sometimes we may be interested in estimating the causal effect of multiple variables at the same time. Then the causal model will include a vector of causal variables, and there is a vector of causal effects that we want to estimate. Here, U, the error term, still stands for all the unobserved excluded vectors, factors that contribute to the generation process of Y. And U is normalized to have expectation 0. Among the multiple causal variables, people often distinguish the exogenous causal variables from the endogenous causal variables. Some of the causal variables may be exogenous and some of them may be endogenous. What that means mathematically is the following. The endogenous variables are the ones that may be correlated with the error term U, and the exogenous variables are the ones that are not correlated with the error term U. So literally, exogenous means generated from outside of this causal model. So the exogenous variables are generated from factors not in this model, and therefore we argue that it's not correlated with U, which include the factors in this model, in this generation process of Y. Well, on the other hand, endogenous variables may be generated also according to some of the factors in the Y model. So that's the distinction of endogenous and exogenous. And the mathematical definition is related to how they are correlated with the error term. Endogenous variables are correlated with the error term, while the exogenous variables are not correlated with the error term. Let's consider an example. Here, let's suppose that Y is log of O, and O is a random variable that stands for the output of a firm. And suppose we're studying the production function of the firm, and if we assume that the production function is Cobb-Douglas in the labor input and capital input and productivity, which means that the output equals productivity times L to the power beta L times K to the power beta K, where beta L and beta K are the labor elasticity and beta K is the capital elasticity. If production function is assumed to be this Cobb-Douglas, so that's our production model, our model for the production of the firm. And if we take logarithm on both sides, we're gonna get log of O equals log of A plus beta L log of L plus beta K log of K. Then if we take the expectation of log A as beta 0 and the demeaned version of log A as U, and we let this be Y, we let this be X, let the vector formed by log L and log K be the vector of explanatory variables. So productivity is unobserved, but labor input and capital input are observed. All right, so this is a model with two causal variables. And in this model, y equals beta 0 plus beta 1 prime x plus u, where beta 0 is the expectation of the log of productivity. Sometimes, depending on the timing of the decision, labor input decision and capital input decision of the firm, it is sometimes reasonable to assume that K is independent of A. So capital stock is determined before the productivity shock is realized for this period. So it's often reasonable to assume K is independent of A, but L is chosen according to the capital stock and the productivity. So L is not independent of A. So within this vector of causal variables, some of the elements are not independent of the error term, and some other elements are independent of the error term. So log of L is endogenous, log of K is exogenous. So we can let, so the endogenous x vector will be this one-dimensional vector log K, and the exogenous x vector is the one-dimensional vector formed by log L. So that's an example of a causal model with multiple causal variables, some of which are exogenous and some of which are endogenous. So we have a model with both endogenous and exogenous causal variables. If we do an OLS of y on all of the x variables, we get some OLS estimators. These OLS estimators typically are not consistent. Even the estimator for the exogenous variables is not consistent. So what that means, what that says is that the endogeneity of some of the causal variables will affect the consistency of OLS estimators for all the causal effects. Even if there is only one endogenous variable, that endogeneity can cause the OLS estimator for all the coefficients, all the causal effects to be inconsistent. That typically is the case whenever the endogenous variable is also correlated with the exogenous variables. Now, I'll just illustrate that point using a simple example. In this simple example, we have only one endogenous x and one exogenous variable, exogenous x. So we're going to ignore this arrow on top of the x because they are now scalars in this example. So the causal model contains one endogenous causal variable and one exogenous causal variable. Let's suppose in this simple example, we assume that exogenous variable is very exogenous, is independent of u. So clearly it's also orthogonal to u. It's also has zero correlation with u. And also suppose in this example, the endogenous variable is not independent of u, but instead is generated by the exogenous variable and the structural error u. Just for simplicity, let's assume this is the case. for this example. Okay, so endogenous variable is generated by the exogenous variable and the structural error in this particular way. So clearly, XEN is correlated with U. Now, we want to know if we run OLS regression of Y on these two, what are we going to get? What are the OLS estimators converging to in probability? In order to know what the OLS estimators converge to in probability, we're going to consider the projection of Y on these two variables. So why do we consider projection? Because we know the projection coefficients are the probability limit of the OLS estimators. Okay, the OLS estimator always consistently estimate the projection. So we study the projection of Y on XEN and XEX. Recall that Y equals beta 0 plus beta EN XEN plus beta EX XEX plus U. Now projection of that, we plug that in here on XEN XEX will be equal to projection of each of these terms on the same two variables. Projection of beta 0 is beta 0. Projection of beta EN XEN is beta EN XEN. And projection of beta EX XEX is beta EX XEX. The last term is projection of U on XEN XEX. Now, what is this? Remember, in this simple example, we said XEX is independent of U. So that is the good variable, but XEN is generated by XEX and U. So we assumed these two things for this simple example. Now, we're going to have to use this relationship to see what U is, given XEN and XEX. So U is related to XEN and EX in this way. U equals XEN minus XEX. So projection of U given XEN and XEX, so projection of U on the space of XEN, XEX, is projection of XEN minus XEX given on EN and XEX. Well, since this is a deterministic linear function of the variables we're projecting on, this projection equals this non-random linear function of those variables. Right? So it equals itself, equals XEN minus XEX. So what we have is projection of Y on XEN, XEX equals beta 0 plus beta EN XEN plus beta EX XEX plus XEN minus XEX. So if you collect terms, you find in the projection equation, XEN has coefficient beta EN plus 1, and XEX has coefficient beta EX minus 1. So the projection coefficients, which are the probability limit of the OLS estimators, are not equal to the causal effects we are interested in for both of the variables. So that's exactly what I went through. So projection of y on xen, xex has beta en plus 1 as the coefficient for xen and beta ex minus 1 as the coefficient for xex. And we know OLS is consistent for projection, so the OLS coefficient for xen converges in probability to beta en plus 1, and that for xex converges to beta ex minus 1. So the OLS of y on xen, xex are not consistent for either beta en or beta ex. So the endogeneity of one variable affects the consistency of the OLS estimator for both variables. All right, so how do we deal with the endogeneity problem in this multiple variable, multivariate causal model? Now let's come back to the general form where we got a vector of endogenous variables and a vector of exogenous variables. Now also suppose that we have a vector of instrumental variables V. So this is a vector of instrumental variables, which satisfies the exclusion restriction, which is the exogeneity condition. What's the exclusion restriction? The exclusion restriction is basically the exogeneity, so it requires V to be uncorrelated with the structural error term U. Why is it called exclusion restriction? It's called exclusion because in a sense that V is uncorrelated with U, V may not be factors included in U, and which means V should not be part of the generation process of Y. So V, generally, when we argue for this condition by arguing that V did not participate in the generation of Y. So V is excluded from the generation process of Y. So this is the sense in which V is called the, so this exogeneity condition for V is called the exclusion restriction. Let's now ignore the relevance condition. We'll come back to it later. Now, with this V instrumental variable vector, the vector of instrumental variables, how do we come up with an estimator? So as before, we want to use the two-state least square procedure. But how do we do the two-state least square? In order to derive the two-state least square procedure, let's start from the causal model as we did before. We're going to project Y on all the exogenous variables, including the exogenous X and the exogenous instrumental variables. So we project Y on V and the exogenous variable X. Doing the projection amounts to doing projection of each term separately and then add them together. So the projection of beta 0 is still beta 0 on V and XEX. The projection on V and XEX for this linear function of XEX is itself And projection of this term becomes beta En prime projection of Xen on Vxex. And projection of U on the two terms will be left here. Now we have obtained this. We want to argue that this projection of U on V and Xex is 0. How do we argue that? It's not so difficult because we know U has expectation 0, and U is uncorrelated with Xex because Xex is the vector of exogenous variables. And also U is uncorrelated with the vector of instrumental variables because we assume the instruments are exogenous. So U has mean 0 and U is uncorrelated with the whole vector that we are projecting on. So that means U is the projection error itself. So the projection is 0. Therefore, the projection is 0. So that shows this projection is 0. This can be crossed out. What we are left with is that projection of y on Vxex is this linear function of Xex in this projection. So if you define this projection as a new random variable, call it Xen projected on Vxex, then this, as in the simple one instrument, one causal variable case, this is part of the endogenous variable X, but it's the good part, the exogenous part of Xen. So this projection picks out the exogenous part of Xen. Why is it exogenous? Because it is a non-random linear function of two exogenous vectors, two vectors of exogenous variables. So this is 0 because it equals some non-random linear function of V and the exogenous X. So that is the good part of Xen. So this suggests that if we can regress y on this variable and Xex together, that OLS regression will give us consistent estimators for beta En and beta Ex. So this suggests if we do observe this random variable, we want to run this OLS regression. And the OLS coefficient will be consistent for the causal effects here, which is also the coefficient in this projection model. However, this projection is not observed. It's something that we constructed. So we cannot directly run this OLS regression, but that is not a huge problem because it is defined to be a projection of an observable on two other observables. We can estimate it using a first step OLS regression of Xen on these two exogenous random variables. So conceptually, it's a two-step procedure, but in Stata, we simply do one step using one command to do it all. So we do IV regress of Y, where Xen is endogenous, and we use V as the instrument for it. And there is also exogenous random variables here. Or you can do the same thing. You can accomplish the same thing by write all the regressors here and write all the instruments here. I believe that is also a correct way to do this regression. Now, we ignored the relevance condition for the IVs, for the instruments. Now let's talk about the relevance condition. What does the relevance condition imply? And where does it come in? In order to see clearly where it comes in, consider this very simple case where there is no exogenous covariates, but there are two endogenous causal variables. There is no exogenous causal variable, but there are two endogenous ones. Then the projection of y on all the exogenous variables, which is the vector of instruments now, will be given by beta 0 plus beta 1 projection of x1 on V plus beta 2 projection of x2 on V, where beta 1 is the causal effect of x1. So the causal model is beta 0 plus beta 1 x1 plus beta 2 x2 plus u. If you do a projection of y on V, you're going to get beta 0 plus beta 1 projection of x1 on V plus beta 2 projection of x2 on V plus projection of u on V, but projection of u on V is 0 because V is exogenous. So what we want to do in the second stage, if we observe these two projections, we would be regressing y on these two projections, right? But we don't, so we estimate these projections and regress y on these two estimated projections. Let's ignore the estimation part because the estimation is good enough for our estimator to still be consistent. So clearly we want there to be no perfect multicollinearity for this among these two variables and the constant, right? Because if there is perfect multicollinearity among these variables, then the second stage where we regress y on these two projections will not be good, right? Perfect multicollinearity cause OLS estimator to be ill-defined. So we do want there to be no perfect multicollinearity. That turns out to be where the relevance condition comes in. A necessary condition for there to be no perfect multicollinearity among these three random variables is that the number of IVs has to be at least as large as the number of endogenous random variables. So that turns out to be a counting exercise. So why is it the case? So projection of x1 on V and projection of x2 on V are both linear functions of V. So let's say this is gamma 0 plus gamma 1 prime V, and this is delta 0 plus delta 1 prime V. We want this, and the constant to not be perfectly multicollinear. Clearly, we want gamma 1 to be non-zero and delta 1 to be non-zero, right? If gamma 1 is 0, then this is a constant. which is perfectly multicollinear with the constant. But that is not enough. We also want these two to be not perfectly multicollinear, and we also do not want the difference between any multiples of these two to be a constant. Okay, so it's not enough to just require gamma 1 not equal to 0 and gamma 2 not equal to 0. We in fact want there to be enough difference between these two linear combinations. And enough difference will imply that this V vector needs to be not a scalar, need to contain at least two not perfectly multicollinear components. So the number of IVs should be at least as large as the number of endogenous random variables. In this example, there are two endogenous random variables. V should contain at least two variables. To see why that is a necessary condition, we can prove by contradiction. Suppose that it doesn't hold. Suppose there is only one instrumental variable. Okay, suppose that the vector of instrumental variables contains only one scalar random variable V. Remember, we have two endogenous X, but now suppose we only have one V. Then what are you gonna do? What's gonna happen? What's gonna happen is the following: the projection of X1 on V is this linear function of V, projection of X2 on V is this linear projection. And necessarily, there will be a perfect multicollinearity among these three random variables, these three components. Okay, why is that? We can discuss. If, say, gamma 1 equals 0, then the second random variable equals gamma 0 and equals gamma 0 times 1 equals gamma 0 times the first element. So there is a non-random scalar that connects this second component to the first component. So there is a perfect multicollinearity between these two if gamma 1 equals 0. Now, if gamma 1 is not 0, then clearly V equals gamma 0 plus gamma 1V, which is the second component here, minus gamma 0 divided by gamma 1. So we can put gamma 1 on the bottom because it is not 0 in this case. And that implies delta 0 plus delta 1V, which is the third component, and that equals delta 0 plus delta 1 divided by gamma 1 times gamma 0 gamma 1V minus delta 1 divided by gamma 1 times gamma 0. See now? There is a perfect linear relationship between the third component and the second component and the constant. So there is perfect multicollinearity in both cases. So when there are two endogenous variables, we need two instruments. Now, that's what I just explained. Now consider a different case. This is also a simplified case, not the most general case, but it's a different special case. In this case, consider that we only have one endogenous variable, but there may be a vector of exogenous variables. And let's see what's the relationship between the instruments and the exogenous variable. What relationship can V has with XEX? Recall that our second stage regression is regress Y on this approximation of the projection of XEN on VXEX and XEX. So for this regression to work in asymptotically, we want this projection and XEX to be not perfectly collinear. So clearly we do not want this projection to be perfectly collinear with the exogenous variables. So this projection, by definition, it is a linear function of V and XEX. By definition, there exists gamma 0, gamma 1, and gamma 2 such that these hold. So this projection equals a linear function of V and XEX. We do not want this to be perfectly collinear with XEX. What that implies, gamma 1 cannot be 0. Gamma 1 cannot be the 0 vector. What that means is, first of all, this V cannot be one of the included exogenous variables, and it cannot be a linear combination of the included exogenous variables. And also, XEN should still be correlated with V even when we control XEX, even after we control XEX linearly. So these are the three implications. So first, V cannot be, so not all the V's, so or in other words, at least one component of V is not a perfect linear, not a linear combination, not a perfect linear function of XEX. So there must be an excluded V that's sufficiently different from the included exogenous variables. And also XEN must be correlated with V after linearly controlling for XEX. So there are two requirements for the instrumental variables, and these are the relevance condition. All right, so we'll not talk about the most general case because the idea is basically the same. Usually we don't include any linear combination of XEX as the instrumental variables. Usually we require So we always require the number of variables in V to be at least as large as the number of endogenous X. So finally, we are ready to estimate the supply-demand model that we introduced at the beginning of the discussion of causal models. And the supply-demand model, the linear version of the supply-demand model we constructed looks like this. So here, Q is the observed equilibrium sales quantity of a market, and P is the observed equilibrium price of that market. And the WD are the demand shifters, observable demand shifters, maybe the income level of the market or the population of the market. And UD include the unobserved demand shifters, like the culture norm of the market or the weather of the market and so on. Suppose we don't observe those things. And WS are the supply shifters. WS and US are the supply shifters. WS are the observable ones and US are the unobservable ones. Supply shifters are typically the cost-related factors that affects the firm's supply given price level. In this supply-demand model, the demand and supply shifters are typically assumed to be exogenously given, while the price and the quantity are results of the demand and supply system, because both of them are are results of the equilibrium. Okay, that is, the price and the quantity, the two random variables, are determined simultaneously by these two equations that have to hold simultaneously. And that's why this system of causal model, the causal model that include a system of equations that has to simultaneously hold and determine multiple endogenous variables simultaneously, we call that system a simultaneous equation system. So this is an example of a simultaneous equation system, or SES. So this is a bit different from all the causal models that we have talked about, because now we have two causal equations instead of one. But we're going to see that we can treat them separately. The variables P and Q, price and quantity, are determined by the system, and therefore they are literally endogenous. We can literally see that by working out the reduced form of the system. So what's the reduced form of the system? The reduced form of the system is the equations that we obtain when we write P as a function of the demand and the supply shifters, and Q also as a function of the demand and supply shifters, but not the function of each other. So we solve for Q and P from that system and obtain those equations, and those equations are the reduced form of the system. So how do we solve it? We can look at these two equations. In order to solve for Q and P, we can set the right-hand side of the two equations to be equal. So we have beta 0D plus beta PD P plus beta D WD plus UD. We set that equal to beta 0S, the supply side equation, plus beta PSP plus beta S WS plus US. Now there is only one variable to solve for from this equation. So we assume that the price doesn't cancel out on the two sides. Assume that beta PD is not equal to beta PS. Typically, beta PD is how demand response to P is typically negative, and beta PS is how supply responds to P, and that's typically positive. So it's not too outrageous to assume that they are not the same. They typically do not even have the same sign. Assume that is the case, then we can solve for P. We move both of the P terms to one side and move the rest to the other side, right? So what we are going to get is P equals 1 over beta PD minus beta PS, beta 0S minus beta 0D, plus beta S WS minus beta D WD, plus US minus UD. So you see, this is how you solve for P. So you write P as a function of the demand and supply shifters. And similarly, you can plug that into one of the equations to obtain Q, and Q will be beta 0D plus beta PD divided by the difference of beta PD and beta PS plus beta DWD plus UD. Okay, and you can certainly simplify that to write it into a shorter form. But what's important is that P now depend, as you can see, P is a function of both the unobservables from the supply and the demand equation. Same thing for Q. Q is also a function of both US and UD. And US and UD both enter P in their whole form. So this is the simplified version of P and Q. So both P and Q depend on both US and UD simultaneously. Both P and Q are also affected by both the demand and the supply shifters, the Ws as well. So both the observable, I want to say the observable demand and the observable supply shifters, which are the Ws. So so these two things are what we learned from writing the system in reduced form. Now come back to the SES. Because P depends on both US and UD, P depends on UD. So P is endogenous. It's not uncorrelated with UD. It's correlated with UD. And P is also correlated with US. Therefore, OLS regression of Q on P will not give us a consistent estimator for either beta PD or beta PS or beta D or beta S. OLS regression of Q on P and the Ws will not give us consistent estimators for the causal effects in this simultaneous equation system. In fact, control variable approach is unlikely to work. Remember how control variable approach works? Control variable approach works by restoring exogeneity of the variables controlling for some other control variables. But because UD enters completely into the generation process of P, unless you can condition on UD itself, it's unlikely that you can restore exogeneity of P at all, conditioning on anything. Because whatever you condition on, as long as there is some randomness of UD left after you condition on that variable, that randomness still enters the generation process of P and makes P endogenous. So control variable approach is typically not working for simultaneous equation system. So how do we solve this problem? We're going to use the instrumental variable approach. In fact, the system, even though the system creates the endogeneity problem of P, the system also suggests some natural choices for instruments, also suggests some potential solutions to the problem. So because we assume WD to be exogenous and WS to be exogenous, WD cannot be instrument for P in the demand equation because they are already included in the causal model. But the variables in WS that are not in WD are valid instruments because they are exogenous by assumption. We assume they are independent of the use. And by the reduced form calculation, we know WS enters the generation process of P. So WS does affect P. That's even when we fix the value of WD. So WS has extra correlation with P even when we control for WD. So the variables in WS, if they are not in WD, are valid instrumental variables. And that's exactly how we solve the simultaneous equation problem. So if there are variables in WS that are not in WD, if there are supply shifters that are not also demand shifters, then those variables can be used as IV for P in the demand equation. That is, they can be used as IV in a two-state least square procedure to consistently estimate the causal effects in the demand equation. Okay. And similarly, when we want to estimate the supply equation, we're going to want to use the variables in WD that are not in WS as IVs. Okay, so in the end, what we can do to consistently estimate the simultaneous equation system is as follows. Let the variable in WS supply shifters that are not demand shifters be supply but not demand shifters. So WS not D. Then we can use the following two-stage least square regression to get consistent estimator for the coefficients in the demand equation. So what we do is to IV regress Q on P using the excluded supply shifters as the instrument controlling for the demand shifters. And analogously, if you want to estimate the supply equation, you're going to need variables in the demand shifters, but not supply shifters. Okay. Use those variables as the instruments for P. So you need demand shifters that are not supply shifters to instrument for the P in the supply equation. Okay. So you see the two-state least square estimate regression is quite useful for solving a bunch of problems. And here we are using it to solve the simultaneity problem in the simultaneous equation system.